Network log architecture. In this video, we are discussing about the network log architecture types, its common pitfalls and strategies, and analysis tools. First of all, we are discussing about the network log architecture. The forensic quality of retained logs and the strategies and the methods for obtaining them are strongly influenced by the environment's network log architecture. There are essentially three types of log architectures: local, remote, decentralized, and centralized. First of all, we are discussing about local network log architecture. In network log architecture, logs are collected on individual local hard drives. This is extremely common because it is the default configuration for most operating systems, applications, physical devices, and network equipments. However, local log aggregation presents issues for forensic applications, such as collecting logs from different systems can be a lot of work. In some cases, log collection causes modification of the local system under investigation, which is certainly not desirable. Logs stored locally on a compromised or potentially compromised system may be modified or deleted. So, even if there is no evidence to indicate modification, logs stored on compromised systems cannot be trusted. Time skew on disparate local systems is often significant and can make it very difficult to correlate logs and create valid timelines. Typically, logs stored on local systems are not centrally configured, and the output formats may vary between systems. Only a limited amount of logs may be stored to conserve local disk space. Next is remote decentralized. Logs are sent to different remote systems throughout the network. So, different types of logs may be stored on different servers. This is commonly seen in environments where there is a decentralized management of IT resources, such as in universities where individual departments or labs manage their own small groups of servers. Remote storage of logs increase their forensic value. When logs are sent to a remote system, they are far less likely to be affected by a local system compromise. At the very least, they cannot be altered or modified after they are sent, unless the login server is compromised as well. Time skews can be partially mitigated by having the login servers timestamp incoming logs. Collecting logs from a login server is usually far less work than collecting logs from endpoint devices, especially since the login server is more likely to be under direct administrative control. Sending logs to a remote server across the network introduces new challenges, namely reliability is the primary concern. If there is a network outage, the logs may be dropped and lost forever. So, reliability is the primary concern, and security is also a concern. That is, when transmitted in a clear text, as in most common, an attacker on the local network may be able to intercept, read, and perhaps even modify logs in transit. These issues can be addressed through the use of protocols that provide support for reliability, such as TCP or RELP, and encryption protocols such as TLS. TCP you already know about, Transmission Control Protocol. The RELP means Reliable Event Logging Protocol. It's a networking protocol for computer data logging in computer networks, and it extends functionality of the syslog protocol to provide reliable delivery of event messages. It's most often used in environments which do not tolerate message loss, such as financial industry. And the TLS, Transport Layer Security, is a widely adopted security protocol designed to facilitate privacy and data security for communication over the internet. However, the configuring support for security features can be difficult, and the network administrators in a decentralized environments often do not have resources to address these issues. Next one is centralized network log architecture. Here, Logs are centralized and aggregated on a central log server or a group of synchronized centrally managed log servers. For the purpose of network forensics, a centralized logging infrastructure is typically the most desirable for the following reasons. That is, the logs are stored on a remote server where they are not subject to modification or deletion in the event of an endpoint device compromise. Time skew can be addressed by stamping incoming logs as they arrive. Furthermore, when logging configuration is centralized, endpoint devices can be configured to maintain synchronized time and include granular time information on log output. Centralized management typically allows for easy access to log data and also facilitates on-the-fly configuration changes when needed to support an ongoing investigation. And the issues of reliability and security of logs in transit can be centrally addressed. That is, the network administrators can configure support for TCP, RELP, TLS and other security features in central logging servers and centrally controlled clients. And aggregated logs can be easily analyzed using centralized log aggregation and analysis tools. And central logging servers are simply servers configured to receive and store logs sent by other systems. They often store logs from many sources including routers, firewalls, switches and other servers, and it enables investigators to find a wealth of data in one place. The evidence stored on a central logging server varies greatly depending on what systems were sending logs to it. Typically, it includes logs from many servers and workstations, operating systems. Next one is remote logging, common pitfalls and strategies. Automated remote logging is generally considered the best practice in log management industry. However, from a forensic perspective, there are potential pitfalls to keep in mind and the ways that investigators can compensate. When event logs are sent across the network to a central server, they are placed at risk of loss or modification in transit. In addition, the forensic investigators must consider issues such as time skew and confidentiality of the event logs in transit, etc. The major factors to consider when event logging is employed in a network forensic investigation includes reliability, time skew, confidentiality and integrity. Now we are discussing each one. First of all, reliability. The logs can be lost as they are transmitted across the network. For example, the clients that rely on the traditional syslog daemon to send logs across the network must rely on UDP as a transport layer protocol. And as you all know, the UDP is a connectionless protocol that does not include support for reliable transport. When a syslog message is transmitted across the network via UDP, if the datagram is dropped in transit, the server will have no record of it and the client will not know to retransmit. So, UDP datagrams are also commonly dropped when receiving application is overloaded due to high volume of traffic. For forensic investigators, reliability of event log communication is an important issue. With unreliable event logging architectures, it's possible for an attacker to execute a denial of service attack or initiate a network outage in order to prevent critical information from being logged on a central server. And accidental loss is also a problem. To address issues of reliability, offshoots of the syslog daemon have added native support for transport of syslog messages over TCP. TCP is a connection-oriented protocol with built-in support for reliability. So, if a packet is dropped in transit, the server will notice a missing sequence number or the client will not receive an acknowledgement of transmission and will resign. Although TCP improves reliability at transport layer, there is still higher layer issues. To address this issue, a lightweight RELP is designed to ensure reliable transfer of syslog messages at a higher layer. Next is time skew. The time skew between endpoint systems is one of the biggest challenges for forensic investigators. It's difficult to correlate logs between endpoint systems when local clock times are off. The best way to manage this problem is to synchronize clocks on all systems using NTP or similar system. NTP means Network Timing Protocol. It's used for synchronization. This can prevent problems due to clock skew during subsequent log analysis. Not all devices support time synchronization, however. Another option is for the central event logging server to add a timestamp to logs as they arrive. Logging output formats may not include enough information to properly correlate timestamps between different systems. When configuring log output formats for potential forensic use, make sure to include complete high precision timestamp with time zone information. Next is confidentiality. Event logs can reveal extensive amount of information about user habits, system software and directories, security issues and more. So they are highly valuable for forensics. Anyone with access to the LAN, whether it is wired or wireless, or a device on the network path may be able to capture and analyze the traffic. To maintain the confidentiality of the event logs in transit, use a protocol such as TLS or SSL that ensures the data is encrypted as it is transmitted across the network. That is integrity. Ensuring the integrity of event logs in transit is extremely important. By default, most remote logging utilities do not provide any assurance for integrity. Event logs transmitted over the UDP or TCP without high alert encryption may be intercepted and modified in transit. Also, an attacker can inject fake event logs into the network traffic. This is quite easy to do for many types of remote logging servers such as traditional syslog servers listening on the UDP port. Now, many event logging architectures support TLS and SSL either natively or through the use of tunneling proxies. So, we can use TLS or SSL to protect the data in transit and mutually authenticate the server and client event logging systems. Next is log aggregation and analysis tools. There are many tools available to facilitate log aggregation on central systems. Log aggregation tools typically work in a client-server model. Typically, an agent is installed on the endpoint system. A compatible central logging server is set up to listen on the network and receive logs as they are transmitted. Often, the central logging server software also includes powerful analysis capabilities. The common agents installed on the endpoints include syslog and derivative daemons such as syslog-d, syslog-ng likewise, and system intrusion analysis and reporting environment. It's also called SNARE. It's an open source agent for Windows, Linux, Solaris and more. And the central aggregation and analysis softwares includes Splunk. Splunk is a log monitoring, reporting and search tool, and another is System Center Operations Manager, SCOM. Formerly it's known as Microsoft Operations Manager, MOM. It's a monitoring and log aggregation product designed for Windows systems. Next is Distributed Log Aggregation for Data Analysis, DAT. It's an open source log aggregation and analysis tool released under GPL, that is GNU General Public License. And next is Cisco's Monitoring Analysis and Response System. It's also called MAS. It's a security monitoring system for network devices and hosts including Windows, Linux and Unix. Next is ArcSight. It's a commercial third-party log management and compliance solutions. Next is Splunk. It's a central aggregation analysis software. So Splunk is a proprietary, portable, highly extensive log aggregation analysis tool. It is inexpensive and versatile, scalable and popular. Inexpensive means it's free for individual use up to 500 MB per day. And Splunk has a web-based interface and a database on the backend. It can accept input in a variety of forms, from reading a flat file to directly receiving syslog data over the network. Once Splunk has processed the data, we can run searches and reports. Thank you.